Hey folks, it's been a while. Sorry about that, but this shit is kind of stressful. I've also been away for a while because this last weekend I was a part of this awesome conference on the doctrine of discovery. We'll talk about that a bit more in our next video. Today, we're finishing up the series of these videos on STEM disciplines during the Islamic Golden Age. Again, today we're talking about some reflections on the achievements of the Islamic Golden Age, Part 3. And just as a reminder, here's the outline of the almost 1400-year history of the Islamic Golden Age that we started with. This period begins with the life of the Prophet Muhammad when he founded the religion of Islam itself, first with only the support of family members like Khadija and Ali. By the end of his life, though, he had united the Arabian Peninsula under Islam. This development of religion, of the Ummah, the Islamic community, of culture, and an intellectual scene continued under the Rashidun Caliphate of Abu Bakr, Umar, Uthman, and Ali, which saw the standardization of the Quran, the development of Hadith studies, and the development of fiqh, the study of Islamic law as it's derived from the Quran and the Sunnah. And after the Rashidun Caliphate came the Umayyad Caliphate, which we talked about the fact that it significantly spread the reach of the Islamic Empire, as well as developing an even further intellectual scene, especially under the leadership of the Caliph Abd al-Malik. And after the Umayyads came the Abbasids, who we talked about in much greater detail in Part 2. But during the Abbasid Caliphate, there was a rival Shia Fatimid Caliphate, which we'll talk about in greater detail today. It's also important to note, though, that after the sack of Baghdad in 1258, there's still 600 plus years of significant work in the Islamic Golden Age under civilizations like those headed by the Mamluk Sultanate and the Ottoman Empire. Today we're focusing on the fourth of these, the Shia Fatimid Caliphate, which came to power just after the Abbasids and came to rival the power of the Abbasid Caliphate. So here on this map we see the extent of lands that the Fatimid Caliphate would ultimately rule over, but they began in this green area in modern-day Tunisia and were eventually centered around modern-day Egypt, where they founded the capital city of Cairo, which was near the very famous ancient Egyptian city of Memphis. In this new city of Cairo, they also founded the still functioning Al-Azhar University and Al-Azhar Mosque, which greatly contributed to the development of intellectual life. Something which was not unique during the Fatimid Caliphate, as like the Abbasids with their House of Wisdom in Baghdad, the sixth Fatimid Caliph al-Hakim also formed a House of Wisdom in Cairo. Today our focus is going to be on one of those scholars that the Caliph al-Hakim brought to the Cairo House of Wisdom, in particular Ibn al-Haytham. Now, we've talked about Ibn al-Haytham once or twice before in earlier videos. Today, it's time to focus on why his work is so significant that he keeps coming up. Although born in modern-day Iraq, Ibn al-Haytham did his most famous work in Cairo after he was brought by al-Hakim to manage the flooding of the Nile. Interestingly, his work in Cairo was built off of the work of a number of different scholars from the Baghdad House of Wisdom. Given that we've primarily been focused on mathematics up to this point, it's interesting to note that one of the places that Ibn al-Haytham made significant contributions was in the realm of geometry. Something you may not know is that geometry has had some significant controversy throughout its history. The vast majority of those who have worked in this area have thought that Euclidean geometry is the correct system to use when trying to describe the actual world. That said, some of the most important advances in the history of mathematics have been in non-Euclidean geometry. The difference between these can be seen with this diagram where we have a line and one point not on that line. In Euclidean geometry, there is one and only one line that goes through that point, which is parallel to the initial line, like this one here. In non-Euclidean geometry, there can be no such lines parallel to the original line, up to infinitely many lines through that point parallel to the original line. Like almost everybody working in geometry around the world for roughly 2,000 years, Ibn al-Haytham actually tried to prove that Euclidean geometry was the correct geometry. He went about this in such a way that he ended up proving some of the first results in what would become non-Euclidean geometry. He did so by working with a very important shape that we now call the Lambert quadrilateral. Note, though, that this is a very Eurocentric name for this object, as the Swiss mathematician Lambert studied this shape almost 700 years after Ibn al-Haytham had been working on it. So what we should call the Ibn al-Haytham quadrilateral looks like the following, with 3 right angles. You might say, well, quadrilaterals have 360 degrees in them, so if there are 3 right angles that add up to 270 degrees, that 4th angle must be 360 minus 270, namely 90 degrees. But it turns out that those things are only true in a Euclidean geometry. So what Ibn al-Haytham was trying to do was prove that that last angle had to also be a right angle. He did so by using a particular argument form known as reductio ad absurdum, where we suppose a particular thing were true, reason as though that thing is true, to try to get to some absurdity, some contradiction, that allows us to conclude the opposite of what we supposed, since these contradictions, these absurdities, can't possibly be true. So Ibn al-Haytham supposed that that last angle was not a right angle and tried to derive some absurdities from that to ultimately conclude that it must be a right angle, and in doing so actually reasoned to some of the very first results in non-Euclidean geometry. What's cool here is that as counterintuitive as the idea of non-Euclidean geometry is, it's been put to really important work in modern physics, most notably with respect to the fact that it's incorporated into Einstein's special theory of relativity. So it should be no surprise that some of Ibn al-Haytham's greatest contributions were in 2 subdisciplines of physics, namely optics and astronomy. Ibn al-Haytham's most famous work was the Kitab al-Manadhir, which translates to the Book of Optics, where optics is the study of the behavior and properties of light and vision. As you can see here from this figure, it's very natural to model our lines of vision using geometric shapes. And when Ibn al-Haytham came on the scene, there were 2 different ways that people tried to describe vision: the extramission theory and the intromission theory, which can be overly simplified in terms of thinking of the lines in this figure as going in different directions. For the extramission theorists, those lines start at the eye and go out to the object, and that's what allows us to see the object. For the intromission theorists, those lines start at the object and go into the eye, and as Ibn al-Haytham realized, eventually to the brain. In his work on optics, Ibn al-Haytham did things like establish the rectilinear propagation of light, that is, the fact that light tends to travel in straight lines, with the exception of cases of refraction, which Ibn al-Haytham also worked on, but also gave early accounts of things like the camera obscura and shadows. This work has established Ibn al-Haytham as the father of modern optics, but importantly, this is not the only contribution Ibn al-Haytham makes. As Omar argues in a 1979 paper, the Book of Optics made significant contributions to the philosophy of science, as questions like the problem of the origin of scientific principles was raised seriously and vigorously for the first time only in the introduction of Ibn al-Haytham's Book of Optics. There, Ibn al-Haytham puts forth a scientific method, which in Eurocentric retellings of the history of science supposedly didn't come around until 600 years later with the work of Francis Bacon. But in Ibn al-Haytham's work, we find what are thought to be staples of modern scientific methodology, like empiricism, the view that our ultimate source of evidence in science is evidence from our senses, that we then use mathematical reasoning on. We find the idea that inductive reasoning, spotting patterns in past experience and making predictions about new cases, is central to science. We find an unbelievable focus on experimentation as the key for testing the truth of scientific theories. But we also find something thought to be much newer, namely a naturalist approach to science, where scientific results themselves tell us something about the philosophy of science. As Ibn al-Haytham was led indirectly to epistemology through his work on the physiology and physics of human vision. That is, he recognized since we use our senses to gain scientific knowledge, results in optics will be relevant to considerations in epistemology of what we know and how we know it. So again, some of Ibn al-Haytham's greatest contributions came in mathematics, optics, the philosophy of science more generally. But before we finish talking about him, we want to talk a little bit about his contributions in astronomy as well. Because when we're talking about the history of the Islamic Golden Age, astronomy is absolutely central here. There's perhaps no culture that has ever contributed more to the history of work in astronomy than cultures during the Islamic Golden Age. I know I'm running short on time, so I'll be brief with respect to Ibn al-Haytham's contributions to astronomy and astronomy in Islam generally. For starters, Ibn al-Haytham's work was part of the Shukuk tradition, where Shukuk means doubt, and these astronomers were creating doubts about astronomy as derived from Ptolemy. In doing so, Jim al-Khalili argues that Ibn al-Haytham developed celestial mechanics, which significantly influenced the work of later European scientists like Copernicus, Galileo, Kepler, and Newton. This astronomical tradition that Ibn al-Haytham was a part of also included scientists like Urdi, Nasr al-Din al-Tusi, and Ibn al-Shatir, who again would have significant influences on Copernicus's work which set in motion what people refer to as the European scientific revolution. This significant interest in astronomy can actually be connected to the religion of Islam itself. Remember, one of the 5 pillars of Islam is that Muslims must pray 5 times per day facing Mecca. This direction toward Mecca is known as the Qibla, and finding the Qibla is greatly aided with astronomical knowledge. These 5 prayers are also supposed to happen at particular times of the day. Determining when it's sunset, late evening, dawn, midday, or late afternoon is greatly aided with astronomical knowledge. The calendar used during the Islamic Golden Age was also a lunar calendar, so astronomical knowledge about the moon is very useful for that. But it's not just these individual examples that are connected to Islam. George Saliba argues that the distinction between astronomy and astrology was actually connected to the religion of Islam. Here we need to recognize that astronomy is the study of all phenomena and celestial objects that are outside of the Earth's atmosphere, where astrology studies the configurations of these celestial objects outside of the Earth's atmosphere and any influence that they may have on people's behavior and happenings inside of the Earth's atmosphere. But Saliba argues that Islam requires a separation between astronomy and astrology because for Muslims, the idea that objects in space are the things influencing our behavior in our lives rather than our own decisions is a denial of ethical and religious responsibility. So again, I think this is a great example of showing that the idea that religion and science are somehow at odds with one another need not be the case. And if you're interested in these ideas, I'd encourage you to look at Saliba's 2007 book, Islamic Science and the Making of the European Renaissance. So this brings us to the end of our discussion of the Islamic Golden Age and STEM disciplines more generally. Of course, I'm going to have to leave you with some music, and since we're leaving the natural sciences for a while, I want to leave you here with a song that I think gives a brilliant philosophy of science throughout. And again, this is another song by Mr. Liff. This time he's with the Polish ambassador and Ayla Nereo. Check it out.
Why? A usual way we start questions. How we advance through life and learn lessons. Suggestions are made and then explored. I'm positive whatever's negative gets ignored. We're on a mission, can you see that? I float a theory through the air, now can you breathe that? And if you inhale, then you embark upon a tale. Don't grieve over things you leave, just set sail. There's no fail, there is only success when you learn from mistakes you've made in progress. Maybe it's best that we halt this discussion. Sit back and just bathe in percussion.